Morning, everyone. So yesterday we looked at our first example of an electrochemical cell. That cell was known as a voltaic cell. Essentially, it is running a spontaneous chemical reaction in order to provide for you some electrical energy. What we started seeing was we would actually need to separate the container into two half cells. If all the chemicals were in one beaker, it's still the same spontaneous reaction that occurs, but I would have no way of actually tapering off the electrical energy. By separating half the reaction in one beaker, half the reaction in the other, we force the electrons actually to travel through a wire, and we actually utilize our table to actually figure out what the spontaneous reaction itself was. Let me just give you some highlights in reading the table. We have this table here. These are referred to as standard reduction potentials. So pretty much as you read left to right, they are all written currently as a reduction. So we're going to have the strongest guys that are reducing at the bottom. So we're going to actually start from the bottom left and go up. You find your first match. On the table, everything is written as an equilibrium here. But once you find your first match, even if you had other chemicals that potentially could also gain electrons, those ones there would actually be spectators. It's only this bottom one that's actually going to do the reduction. Similarly here, as the chemicals get worse and worse at going forwards, then my chemicals that are oxidized, they call it the reduced species, the chemical before they were oxidized. As I read right to left, the strongest guys are on the top. You're going to find your first match. As long as the reduction is occurring, this whole half equation is lower than the oxidation half equation we're going to have in today's lesson, and E naught that's positive, this is going to be a spontaneous reaction. This is going to be a working battery that the chemical reactions actually generate some voltage for you. So today I just want to qualify a little bit more with this voltage. What is it? How do we do some of the math around it? And just rehash some of the terms from yesterday in looking at this electrochemical cell. So let's just have a look here. You already have that top part filled in from yesterday. Electrons flow because of an electric potential. Potential is another word for voltage. Voltage is essentially the work done per electron transferred. Or you can think of this as, well, as electrons are moving in that external wire from anode to cathode, this is the amount of energy every coulomb of charge is actually carrying. As it travels through the wire, that's actually what's tapered off as electrical energy. This is giving the electrons the push to actually go from anode to cathode. Technically speaking, this potential should not be able to be just for a half cell. If I just have, for example, let's take a look at that copper side again. We have a copper plate and we have copper ions. Yesterday we found that copper ions were actually better at reducing, so they solidified onto copper's surface. The reaction was Cu plus 2 gains 2 electrons. I do the one-way arrow, get copper. I can find this reaction on the table. So we start from the bottom left and go upwards. I find an exact match of copper 2 plus. I actually find it twice. Well, this one here, copper 2 plus, is better at reducing and becoming copper solid than becoming copper plus 1. That occurs at a voltage of 0.34. That's sort of like saying just this reduction already has a push of 0.34. This provides that voltage to the battery. And yet, if I only have copper ions in solution, they can only gain electrons. Who is willing to actually give me the electrons? Remember, a redox reaction has to be both a loss and a gain. So what's going to happen here is we actually have, well, obviously in our reaction from earlier, it was a zinc cell that actually gave it the electrons. But for us to be able to tabulate, to make comparisons between these half cells, what we're going to do, even though we can't do a voltage for one single half cell, we can set up a standard half cell. We can measure a copper half cell against the standard, and we can say, let's say this standard here has 0 volts. If I put copper here as 0.34, that just means it's 0.34 better than the standard. Okay, so these ones here are all relative voltages as we'll see on the table. These ones here are set with an arbitrary hydrogen half cell. Usually for the standard hydrogen cell, we call it the She. The She is our standard hydrogen electrode. Out of all the electrodes I could have chosen, I could have set any reference. I just chose this particular half cell here to be 0 volts. And this is actually smack in the middle of our table here. That's this reaction. H plus ions get reduced to become half H2. That's given as 0 volt. Is this really 0 volts? No. It probably has a voltage of its own. But let's say if we call this 0, and in hooking up with a copper half cell, copper has a 0.34. That 0.34 actually just implies to me that this copper half reaction is 0.34 volts better than the She. Right? So in terms of these two guys here that could reduce, copper ions here reduce 0.34 volts better than H+. Earlier, we did the zinc reaction as well. If you consider the spectator ion zinc here in trying to reduce, how come that was a negative voltage? What good is a battery in providing you negative voltage? It's like eating away voltage. Well, that's actually not a negative voltage. It actually is positive, but it's only negative relative to 0 volts. So this one here, that negative 0.76 just means it's 0.76 volts worse than the She. All voltages here should be positive, but because we set this hydrogen cell here to be our zero value, we can actually have some things that are positive, some things that are negative. So that's an important note for yourself here. It's relative to the standard hydrogen cell here. I'm going to draw you what the standard hydrogen cell looks like. So we're going to have a half cell. Up to this point, we've just had a solid plate in sort of aqueous solution. In this case here, we'll notice at least one of the sides of my hydrogen half cell is actually a gas. So what's going to happen here is I'm going to need a sort of chamber of some sort that can actually bubble in hydrogen. So I'm going to pump in hydrogen gas, or hydrogen gas is actually going to be released. Well, hydrogen gas here, if it wants to drop off electrons, it needs to have somewhere to drop off electrons. I don't have a hydrogen solid plate. So what we're going to actually do here is we're going to actually put on a metal plate. This metal plate here is going to be an inert electrode. The inert electrodes that we have, really we only always talk about two of them. One of them is a carbon electrode, the other is a platinum electrode. Although these ones here, chemically speaking, they might end up oxidizing, but they're so bad at oxidizing that they pretty much don't interfere. These guys here are the best at oxidizing here. The carbon and the platinum here are so far down the table, pretty much something else would have oxidized before it, and therefore it's just a temporary holding place, a temporary conductive surface where the hydrogen can actually drop off electrons. So let's think about the oxidation here. We bubble in some hydrogen. This is going to end up jumping into solution as H+, so the overall solution is going to become more and more acidic, but it's going to drop off its electrons on top of this surface here that is completely inert here. It's just a conducting plate for you. This is the standard hydrogen half cell. Because we do want to make a fair comparison with other equations as well, we do want to set our standard conditions again. That's why we have that not symbol. We have a E, that's for voltage, but we have this not symbol. This not here, as we saw from last year, usually we're going to be at 25 degrees, so that's going to be 298 Kelvin. In the past, it used to be 1 atmosphere. Nowadays, we're going to use 1 bar instead, so slightly less than an atmosphere. For a lot of these things here that are in solutions, we're going to have 1 molar solutions, just like any old battery. As you generally use up the chemicals, the battery gradually dies. We're not going to have the voltage forever. So when the concentrations are at 1 molar, that's when these values have been tabulated. Elements are in the standard state. They're in the most pure, most stable electrode. So that's called an E naught. And there we go. That's your standard hydrogen half cell. That's actually what this voltage is actually talking about. So as we look back at the cell from yesterday, we're going to rehash some of the bits and observations that we did, and we're going to do a little bit more with this voltage as we look to some new questions. So just let me rehash with you from yesterday just for practice. We had 2 half cells. We had 1 half cell here with zinc in a Zn+2 solution. We had 1 half cell with copper, and we had Cu+2 ions. First thing you would do is you would check the table. We want to find who's better at reducing, who's better at oxidizing. We start from the bottom left and go upwards. We find copper is better at reducing, so we're going to do a one-way arrow. Copper 2+ gains 2 electrons, becomes copper. Now we understand that 0.34 volts, that one just means it's better than hydrogen. Now you notice I didn't hook up copper to a hydrogen half cell and then zinc to a hydrogen half cell. I just hooked up a zinc half cell to a copper half cell because both of them are relative to hydrogen and these values are all relative to the same standard. We're okay just comparing these directly. So between copper ions and zinc ions, the zinc ions sit around, they don't do anything. In terms of the oxidation, as you start from the top right, these are the best guys oxidizing. We run into zinc solid oxidizing better than copper solid. So that's when we had the zinc as a metal plate. It's going to jump into solution, become Zn2+, and it's going to drop off its electrons. Its electrons never enter the solution. A reminder here, this zinc ion has nothing to do with the zinc ion that was currently there. I didn't have to have zinc ions in solution. The reaction would still happen. Notice this is the site of oxidation. The Zn has dropped off its electrons, becoming Zn2+. The site of oxidation, the metal plate that's involved, is called the anode. The site of reduction, the metal plate that's involved, is called the reduction. And by setting up these 2 half cells in 2 separate beakers, we can connect these two here with an external wire. Electrons always flow. Electrons flow anode to cathode. For a voltaic cell, the anode is actually negative because we have all these electrons deposited here. If I build up negative charge here, given an option, they're going to want to repel away from each other, run to a side that's actually becoming more positive than it. That's why electrons have this capacity to actually go to the other side. We're forcing electrons to flow in a current, so in one direction here. This top part here is actually where we're going to taper off that electric energy. We're going to stick our light bulbs or whatever buzzers or MP3 player, whatever, for that direct current to actually taper off the electrical energy. The reaction is then going to have copper ions. They're going to swim up close. They're going to pick up the electrons that arrive here, and they're going to solidify as copper solid. Okay. We talked about some observations we can make at each plate. This time, because the solid zinc is actually jumping off into solution, the mass of this anode actually decreases. We're actually getting some of those ions in solution. They're in solution, but they're no longer part of this electrode. The electrode is sort of wearing down. On the other side, the metal plate was already made of copper, and now we're actually solidifying new chunks of copper solid on its surface, so therefore the mass actually increases. Don't memorize that. You can just see that directly from the equations themselves. Okay. We talked about if you did this in the lab, nothing would happen. We're at risk of becoming overly positive because of the Zn2+. We're becoming overly negative on the other side because we're losing copper +2. We need to throw in something to maintain the electrical neutrality. We're going to call this here a salt bridge. It could be a U-shaped tube here containing a solution. I've made a salt bridge before. Just take a piece of paper and just absorb it with water. Usually the salt bridge is made out of 1 molar. There's our 1 molar again so that we can be in standard conditions. Usually it is made out of KNO3. In terms of the table, we would have K plus and NO3 minus. By the time you find K plus, this guy is so bad at reducing, probably someone else has reduced before it. It's going to be a spectator. I don't know if nitrate's on the table, but very similarly here, it should be really bad. Those ones are just spectators so that we have the left-hand side in becoming overly positive. The anions are going to flow towards the anode side. The NO3 minus is going to jump into this solution to try to counterbalance that positive charge. This side here is steadily losing copper +2. It's at risk of becoming less and less positive. The K plus as a positive is going to jump into that solution, and therefore we can make a conclusion. Anions generally flow towards the side with the anode, and then cations flow towards the side with the cathode. This copper solution at first probably would have had some counterbalancing anion. Depending on the size of it, it may or may not be able to go through the salt bridge, but at least there's this general progression. Anions towards anode, cations towards cathode. All electrochemical cells, all voltaic cells are going to look like this. Okay. So what we're going to do in detail here is just practice a little bit more voltage. When you're determining the E cell, the voltage that the battery is supposed to supply, remember these rules. Anytime you reverse a half reaction, the sign is reversed. These voltages are all for reduction potentials. Potential is that other word for just voltage. Careful, potential is different from potential energy. But going from left to right, how much better than H plus is it? Well, it's positive 1.51, positive 1.36. That's positive. But what about going in reverse? What if I wanted the oxidation? If I undo it, if I would have gained positive 1.51 volts, I would have flipped the sign. I would have been negative 1.51 volts going the opposite way. So be careful of that when you're dealing with the half reactions. When you add up the two half reactions, basically, well, one half reaction gives you, this one was 0.34, the zinc reaction. Going left to right, this was as a negative 0.76. Now I'm going right to left. Zinc is actually oxidizing. It's actually going to give me a positive 0.76. That's when I reverse the sign. That was step 1. Now, if the copper reaction gives you 0.34, the zinc reaction gives you 0.76, in total, you're going to just add up the 2 volts, and we get 1.10 volts. Here's an important note. Even if a half reaction ends up being multiplied, you end up doing lowest common multiple, you end up wanting to sort of make sure there's no free electrons in nature, do not multiply the voltage. Why is that? We're going to have this generalization here. Voltage is actually telling me the energy per coulomb of charge, per how many sort of charges actually pass by you. So let's just put some random numbers to this here. Let's say the energy that the charges get in passing through the wire, let's say they get 10 joules for every 1 coulomb of charge that actually passes by. As you multiply the equation, you run the equation twice. So definitely you're going to get twice the energy. But what you're going to find is when you double the equation, every time you double the equation, you actually double the number of charge carriers as well. That's sort of like saying, yeah, we have twice the energy, but 2 coulombs worth of charge, you notice by ratio, it still ends up as 10 joules per coulomb. because this is already defined as a per coulomb of charge, we don't end up scaling up the voltage. So just look out for that there. So I can finish this off here. We alluded to this last day as well. So we're going to write out, we have our copper reaction, Cu plus 2 gains 2 electrons. On the table, it was a two-way arrow. Once we know which direction it is, I want it one way. So this reaction here occurs, I can just read the reduction potential, 0.34 volts, better than hydrogen. The zinc half cell here, zinc was better at oxidizing. The Zn ends up becoming Zn plus 2 and 2 electrons. On the table, this is reduction, left to right, negative 0.76. Going in reverse, it's now going to be positive 0.76. I don't really care about what these half cells voltages are. Usually what I care is the overall battery. The battery is both anode and cathode. We already have Lewis-Common multiples, so 2 and 2 cancel out. So we get copper and zinc become copper and zinc ions. And we're just going to add these two voltages. I believe you get 1.10 volts. This is positive. For voltaic cells, positive means a spontaneous chemical reaction. All right? So that's sort of all the details that we have for this cell here. Let's have a look at an Ag and an Fe half cell. So what would this cell look like? An Ag, so Ag is a silver plate. Usually for a half cell, if there's a silver plate, I'm going to have a silver ion solution. That's going to be one part. The iron half cell, I can have iron as a solid, no problem. Iron is a transition metal. I can have multiple oxidation states. Let's throw in an Fe plus 2 or an Fe plus 3. One of those are going to reduce better than the other. So if you make a list of what we have silver solid, Ag plus, Fe, Fe plus 2, Fe plus 3. So again, we're going to look at our table. Start from the bottom left and go up, find your first match. Okay, I find my first match here. I end up finding the Fe plus 3 right away. The Fe plus 3. So it reduces as a voltage of 0.77. I should just notice I actually run into silver plus first. So even though they're sort of neck and neck here, the Ag plus is still the stronger guy at reducing. It's a stronger oxidizing agent. So it's actually Ag plus that has a voltage of 0.80 that's actually going to do the reduction. So let's try this here. Let's just write out the reaction. On the table is written as a reversible reaction. Ag plus gains an electron, one-way arrow forms silver. I can just read up that voltage, 0.80 volts. We had our silver plus, Fe plus 3. Let's see if there's any other matches, Fe plus 2. So on the reduction side here, because silver ends up reducing, the other two here are spectators. They just swim around solution. What about on the other side? We start from the top right and go downwards. I want to find an exact match. I can start at this iron solid here. Well, this iron as a solid, it's going to end up oxidizing. That's reading right to left. Going right to left here, this one was a negative 0.45 going left to right, so I'm going to need to change it to actually positive 0.45. So going the opposite way here, I'm going to write iron on the reactant side, as iron actually becomes Fe. Oh, this one turns out it becomes Fe plus 2, better than plus 3, and the voltage, I'm going to flip the sign here as positive 0.45 volts. Totally possible that some of these half cells are actually worse than hydrogen, that they're negative. The voltage that I care about is actually the voltage in total when I add the two half equations together. So here we go. We're going to double, because I want Lewis-Common multiple here. I want to double this equation. Technically speaking, you do get twice the energy. So why don't we multiply the half reaction? We do get twice the energy, but we also get twice the electrons. So I just showed you by ratio here, they end up canceling out. I'm just going to show you this equation then. So the overall equation is 2 silver ions. They react with an Fe. They become silver metal. And then we have a Fe plus 2. All right. What's the total voltage? You just add up those two voltages. We just call that E cell. The voltage total is going to be 1.25 volts. Again, that's a positive. That's because your reduction reaction has occurred before your oxidation reaction. Later on in this chapter, we're going to do the same thing. Find the strongest guy reducing, find the strongest guy oxidizing. But by the time you find your match, they would have crossed each other, and those would therefore be a non-spontaneous reaction. Okay. I can ask you for definitions here. I can ask you who gets oxidized, who gets reduced. Well, in this case, I see that the electrons on the left side, this top reaction is the reduction reaction. This one here has gained electrons. This one stole electrons from iron. The iron actually drops off 2 electrons for the Ag. So let's think in the electrochemical cell here. The iron here is going to become Fe plus 2. That has nothing to do with the iron plus 2 and plus 2 that are already in solution. The iron physically becomes even more Fe plus 2, dropping off its electrons. because this is the site of oxidation for the iron. This guy here is called the anode. So iron is actually the anode in this metal plate here. As the electrons here build up, that's the negative side. We get an electrical wire here for the electrons to flow. Electrons flow from anode to cathode. The electrons arrive at the silver side. The silver plate here could care less. It's just a temporary metal surface holding charge. It's actually the silver ions that grab those electrons that came from iron, swims up close to the surface, and basically deposit themselves as silver onto the silver metal plate. So we can call this one here the cathode because electrons flow anode to cathode. That's the site of reduction. The mass increases because the silver solidifies on its surface. One thing's missing is probably a KNO3 salt bridge just to make sure the circuit is complete. Okay, so that's going to be a battery. If everything is at standard conditions at 1 molar amounts, the standard voltage is going to be 1.25 volts. Okay. Notice all the E cell, so in total, so this is reduction and oxidation together. So both parts is positive because positive actually implies spontaneous. So spontaneous reactions, ones that occur without any external influence. Spontaneous reactions provide a positive voltage. And that's what you would actually expect from a battery, right? A battery has a bunch of chemicals inside, and once you plug in the battery, once the circuit is complete, the chemical energy should be converted over to electric energy. So here's just one small note here. There is actually a link between, well, we are talking spontaneity again. Well, we did spontaneity last year based on free energy change. So I'm just going to do this with you here. The delta G of the reaction, the Gibbs free energy change is actually going to be negative NF and this E cell. Let me just define some of these terms for you here. The delta G we know. This one here is change in Gibbs free energy. This was the one that if delta G was less than 0, that was spontaneous. We did that hand wavy derivation with the second law of thermodynamics. The key I want to point out to you is actually this negative. It's actually a different sign. So if I want it spontaneous, if I want this to be negative, I better make sure that the rest of this is positive. Nicely here, N is actually going to be the number of electrons in the balanced equation. So in this case here, we had 2 electrons actually being passed, so the N in that case would be 2. F actually stands for Faraday's constant. You can look up this value. It's going to be some positive value. Faraday's constant is essentially the charge per mole of electrons. Right? So that part there should make sense. If I know how many moles of electron are being transferred, and I multiply it by, this is the charge, this is the coulombs for every mole that passes by, in total this would give you a total charge, and then we're going to multiply the voltage. Charge times voltage gives you energy. And this E cell is actually this potential that we talked about. This is the battery's voltage. Right? So again, I just want to emphasize here that the connection to free energy here, when we wanted delta G to be negative, that means the voltage here has to be positive for a spontaneous reaction. Anytime the total E cell, the total voltages of the 2 half reactions end up actually being negative, it actually is going to be non-spontaneous. So here's our conclusion. For an E cell that's positive, then delta G is actually negative, and our reaction is spontaneous. We have what's referred to as a voltaic cell or a Daniell cell, like we're talking about now. Later on in this chapter, we're going to talk about what if your delta E cell is actually negative. Then if this is negative, negative, and negative becomes positive, and therefore the redox reaction is actually non-spontaneous. That's actually going to be called the electrolytic cell later on. Okay? So there was one more question for you to practice. I can skip over that. Pretty much, I'm giving you, I just have lead and aluminum. If you just had these 2 metal plates, we had talked about in an earlier lesson, no reaction. They can't oxidize unless anyone is willing to pick up the charges. If I have a lead aluminum half cell, I'm sort of implying that it's lead inside a lead solution, aluminum inside an aluminum solution. And then you can check the tables. Start from the bottom left, find the first match. Start from the top right, find the first match. Okay. Now, we're going to do a couple little tweaks here. Let's examine for our original copper half cell again. Let me just rehash with you these reactions. You can, at any point here, just look on the table again. This copper reaction had occurred at a positive 0.34 volts. The zinc reaction, that was actually the higher reaction. This was the one that I actually flipped around. So zinc was actually better at oxidizing. That was at negative 0.76. So zinc becoming Zn plus 2 and 2 electrons. I reversed it, so this is positive 0.76 volts. One other observation I want to make here, examining this original half cell, what's going to happen over time is the concentration of Cu2 plus is steadily going to decrease. Now, last day we had talked about it in context of a salt bridge. If I lose too much positive charge here, the reaction is going to cut off. In this case here, even if I have my salt bridge, my battery is running for a while, over time, the concentration of Cu2 plus is going to decrease. It's going to drop. As I lose reactants, it is going to shift the equilibrium over. It's going to decrease the tendency for copper plus 2 to be reduced. What's going to happen to the voltage then? Well, I needed copper plus 2 at 1 molar to be actually 0.34 better than the hydrogen half cell. As over time I steadily use up the copper ions, they're solidifying to become copper solid. As this concentration decreases, as the equilibrium ends up shifting over again, my tendency to go forwards is actually weaker. So this voltage is actually going to decrease. So voltage actually decreases from 0.34 volts. Right? It's going to steadily decline. The battery is going to slowly deplete itself. And in a similar way, what about concentration of Zn2 plus? The concentration of Zn2 plus actually increases, it actually goes up, because Zn is constantly jumping into solution, it's replenishing, it's making a lot more zinc ions. As the Zn concentration actually increases, we actually, well, let's think about it here. If this concentration goes up, again, these ones here, at the end of the day, they were all equilibria. As we increase the concentration, it actually shifts it to the left. I needed to go right to actually get 0.76, so therefore the voltage also decreases. Both half cells actually decrease from this positive voltage, eventually until when? Until both of their E naughts, they're going to add up to give 0, okay? Because they're both positive to begin with. This one here needs to drop to 0. This one here also needs to drop to 0. So the overall 0 plus 0 is just going to be 0. So eventually the reduction and oxidation potentials will be the same, opposite in sign. So therefore the E cell will be 0. This cell is said to be a dead battery, or we actually have, back to our concept of equilibrium, we've actually hit a balance point where there's no more tendency for me to go forwards anymore. We're at 0 volts. In this case here, because of the signs, both of them are positive. Both of them actually have to drop to 0. We could have a situation here, we're going to compare with silver and zinc. Maybe this one here was actually negative. So if it was like negative 0.4 and the other one was positive 0.4, that would still add up to give 0. That would also be a dead battery. So they both don't need to actually hit 0 themselves, but they do have to be equal and opposite. Okay? So let's try that out for these last couple problems here. Let's examine what happens to the E cell when we're not at standard. Remember, standard had this whole notion we were 1 molar concentrations. That's actually a fairly high concentration. We're actually using lots and lots of chemical for that. So that's why battery engineers would play around with different chemicals, potentially giving you the biggest potential difference so that I'm not wasting amounts of chemical. So what we have in this first description here, we have a silver wire. So I'm just going to make a list of what we have. We have silver solid. We have silver ions in solution, Ag+. There probably is some counterbalancing ion, but they're not telling me what it is. It's immersed. And there's also a zinc strip, so zinc solid and Zn plus 2. I made a list of all my ions. Check your table. Start from the bottom left and go upwards. What's your first match? As you go upwards, I've run into silver first, so that's going to be the reduction at positive 0.80. So silver is going to become, gain an electron, becoming one-way arrow silver, and that reduction potential I can just read right off, 0.80. The zinc solution, start from the top right and go downwards. Those are the best guys oxidizing. I run into zinc solid, so the zinc reaction becomes Zn plus 2 and 2 electrons. That voltage, this is a reduction potential, negative, so I'm going to make it a positive for an oxidation potential. That's going to be 0.16 now. We can do the standard balancing again, least common multiple, 2 times this, so you don't double the voltage. The total voltage is supposed to be these two added. What is 0.8 plus 0.76? This one here gives me 1 point, so the E cell at standard conditions at the working battery here is supposed to be 1.56 volts. Now what if we're not at standard conditions? This all just ends up as almost like a Le Chatelier stoichiometry problem. Experimentally, this is really easy to do. we would have had silver in one half cell, and we have zinc in another half cell. All we're going to do is we're going to maybe let's dissolve in some more zinc. So the silver, I just left it alone, but let's dissolve in somewhere, let's drop in somewhere solid, and let's increase the zinc content. Well, let's think in terms of equilibrium. Artificially beefing this zinc up more than the 1 mole that it was supposed to be would shift the equilibrium over. This one here would not quite give you 0.76. We would expect the overall E cell to decrease. Right? So it's going to be lower than the 1.56 at standard state. What if we did it the other way here? Let's take the silver solution. Let's add a bunch of water. As you add water to it, all those swimmers here now have a bigger pool to swim in. As that concentration ends up dropping, this is going to lower the silver concentration. As it shifts the equilibrium over, again, the E cell would decrease. It's totally possible I could have shifted the equilibrium the other way. Let's say I actually diluted the zinc instead. If I added water to the zinc side, the concentration of zinc here would actually have decreased. That would actually shift the equilibrium over to the right. That actually allows the oxidation to occur more, and it's actually going to be even more than 0.76. So it ends up becoming just a Le Chatelier kind of question. I'm just going to include this here. Diluting Zn plus 2 would shift the oxidation equilibrium to the right, and therefore, for that situation, the E cell would actually increase. So we can temporarily play around with the voltages by shifting the equilibrium by diluting one side or diluting the other side. Okay. So get some practice in reading the table here. There's some standard questions here with the voltaic cell. After you've looked over this one here, tomorrow we'll switch gears and we'll start taking a look at electrolytic cell. Okay. Let me know if you have any questions. Thanks, guys.